Today we're going to look at the Pythagorean theorem, and we're going to look at it on a coordinate plane. And what we're going to do is we're going to be given 4 points, and these points actually we can connect them to form a rectangle. And then we're going to look at the diagonal for the rectangle, and then we're going to use the Pythagorean theorem to find the length of the diagonal. So we're going to start with the points A, 5, 1. So I'm going to bring my graph up here, and I know it said you need a graph paper, but it's on here, and I'm hoping that we've got the same coordinates. If something happens that you've got a paper that's got different coordinates than me, because I brought this home after planning for the sub, change it to these coordinates if it's different. Alright, so we're going to go to 5, 1, so we're going to go 5 on the x, 3, 4, 5, and we're going to go up to 1 on the y. So we're going to plot 5, 1, and I'm going to go ahead and label that A. And then we're going to plot the point 1, 1, and we're going to label that B. And then we're going to label the point, plot the point 5, 6, so we're back to 5, and there's 1, 2, 4, 5, 6, so that's point C. And then we're going to do the point 1, 6, so that'll be up across from the C and above the B. So when I connect the dots, we have a rectangle. And we're going to draw a diagonal, and it really doesn't matter which one. I'm going to go, I forgot to label this D. I'm going to go ahead and do the diagonal from B to C. And we're going to find the length of that diagonal. Since it's a rectangle, the other diagonal, the AD diagonal, would be the same length. So it really doesn't matter which one you use. Alright, so to find the length of the diagonal, we know we have a right angle here. And we're going to look at this right triangle, and we're going to call it BCD. So the length of one side, 1, 2, 3, 4 units. And then the length of the other side is 1, 2, 3, 4, 5 units. Now, if we look at these lengths, we can actually look at the x-coordinates from here to here. We've got an x-coordinate of 1 and an x-coordinate of 5. So if we're going from 5 to 1, from D to C, here's the x and this x. We're actually just subtracting those to get the distance from one to the other, but we can actually count the spaces too, since we have the grid there. Same thing with our y's. And our y-coordinates would be from D to B. So if we look from D to B and look at this y-coordinate and this y-coordinate, they go from 1 to 6, so that's where we get the distance 5 if we take 6 minus 1. So, and I would call these x, y, and then this could be x sub 1, and that could be y sub 2. And the only reason I show you that is because you're eventually going to be doing something called the distance formula, which we're not going to get to this year, but this will help you tremendously when you get to the distance formula. So to find the length of BC, we're going to have to do the Pythagorean theorem. So what we would do is take 4 squared, which is the length of one of the legs, plus the length of the other leg, which is 5 squared, and that will give us the length of the third side, and we're just going to go ahead and call that C, and we'll call that little c squared. Alright, so C is actually the length of the segment BC. So those mean the same thing. This is just the points that it's connected by. So 4 squared is 16, plus 5 squared is 25, and that'll equal c squared. And 16 and 25, this is just the way we solved them before. That would be 41 is equal to c squared. So I'm going to do the square root of 41 on my, or 41, I'm sorry, on my calculator. So I'll hit 41 and hit square root because I've got one of the old TI-30 calculators here. I'll do that again for you. So I'm going to do 41, whoops, and then I hit the square root. On the newer ones, if you have one like in my classroom, you're actually going to hit the square root key, and it's going to give you a place to put in 41, then you would hit enter. So it's going to be approximately 6.40. So when I take the square root of both sides, c would be equal to, squiggly equal signs there, 6.40. And that would be 6.40 units. Alrighty, so our next example, and again, hopefully you have the same coordinates that I do. We're going to do the same thing here. And this is points M, N, O, P, and again, change it to these if yours are different. So we're going to plot the point M, which is 0 on the X, 3 on the Y. And then N, which would be 7 on the X, 1, 2, 3, 4, 5, 6, 7, and 3 on the Y. And then we've got the point 0, -1, so we're 0 on the X, -1 on the Y. And I'm not labeling these, there's M, there's N, here's O, and then P is 7, -1, so that'll be right under the N. Alright, so this, it would be called rectangle MNPO, or NPOM, or POMN. Not MNOP, because they go MN and then we cross over. So that was my fault on that one. Alrighty, so we look at this rectangle. Again, we're going to look at the diagonal. And I'm going to go ahead and do this time the diagonal in the other direction. I'm going to do the MP. And again, we're looking at the length of one of the legs, and actually the two legs. And I'm going to go ahead and use these over here. So we've got 1, 2, 3, 4, 5, 6, 7 is the length of one side, MN, and the length of the other, PN, is 1, 2, 3, 4. And so we are trying to find the length of the hypotenuse, which is C. So again, we're going to look at this and say that we've got 7 squared plus 4 squared equals C squared. Oops, sorry about that. And that's going to be 49 plus 16 is equal to C squared. And when I add these up, I would get 65 is equal to C squared. And if I take the square root of both sides, square root of C is, or C squared is C. And then on my calculator again, I'm going to do 65 and square root that. So that's going to be 8.06, and we'll just round it to the nearest hundredth again. So that's going to be approximately equal to 8.06. And we're just rounding to the nearest hundredth. Alright, so that would be all of those. And tomorrow you'll come in and you're going to do some of these problems, which are fairly simple. And then you'll do some more application problems. Have a good evening.